Let's start with our first example. So we have a circuit shown here. The capacitance is 0.3 microfarad. The resistor is 20 kilo ohm and the battery is 12 volt. So we're going to have many questions here. So you see this is a charging process. First we're going to find time constant, then the maximum charge and time for the charge to reach 99% of the maximum value, and the current when the charge is half of its maximum value. We're going to find maximum current too, and in the last part we're going to find the charge when the current is 20% of its maximum value. Since this is a charging process, let's write down the main equations. So remember, when we discussed charging process, I mentioned two important equations. This is the first one, and we have the charge equation. Charge is a function of time. Or we can re-express this equation in terms of Qmax. Let's keep all these information here. Now, part A is very simple because time constant is R times C. So R is, be careful, this is 20 kilo ohm, so it's 20 times 10 to 3 times capacitor, which is 0.3 times 10 to minus 6. This is microfarad, and the result is 6 10 to minus 3 seconds. Well, part B, the maximum charge, again, this part is also simple. The maximum charge is epsilon times C. Okay, so epsilon is 12, and the C is 0.3 microfarad. So the result is 3.6 microcoulomb. So this is the maximum charge. Now, in part C, we're going to find time for the charge to reach 99% of this maximum value. Let's first try to understand the question clearly. So if you plot Q as a function of time, we have this. So this is the maximum charge, which is 3.6 microcoulomb. So we want to find out the time for this value. I'm looking for this time t here. Well, to find that, of course, we have to use charge equation as a function of time. So since we want to find the 99% of the Qmax, maximum charge, it's better to use this form. So I'm gonna start with this equation. So Q is Qmax 1 e to minus t over RC. Charge is 0.99 Qmax, and on the right side we have Qmax, and we have 1 minus e2 minus t over RC. So Qmax cancel out. So we have 0.99, which is 1 minus e2 minus t over RC. So then we have 1 minus 0.99 on the left side and e2 minus t over RC on the right side. So this is 0.01, and we have e2 minus t over RC. We have to take ln of both sides. I'm going to take ln of both sides. So ln 0.01 is minus 4.69. You can use your calculator. When you take the ln of this part, you will get rid of this exponential term. Then we have minus t over RC, so which is minus t over RC. So here we have the value of RC, 6 10 to minus 3. So from there, t is 28 10 to minus 3 seconds. For part D, we want to find the current when the charge is half of its maximum value. But for that, I'm going to provide two solutions, easy and short one, a long and difficult one. The first solution, but I'm going to have the first solution later. Let me start with the second solution. So again, we want to find out the current when the charge is half of its maximum value. So let's first find out the time for this value of the charge. Okay, so this is Qmax. Now we want to find out time corresponding 0.5 Qmax. Let's first find out that. So for that, I'm just going to repeat the previous calculations. So Qmax 1 e to minus t over RC, and now we have 0.5 Qmax equals Qmax 1 minus e to minus t over RC. Again, Qmax is cancel out, and we have 0.5 is 1 minus e to minus t over RC. Now 1 minus 0.5 is E2 minus 2 over RC. So 0.5 E2 minus 2 over RC. And we have to take ln of both sides. ln 0.5 is minus 0.693. And again, we'll get rid of this exponential term on the right side, which is just T over RC. And we know the value of RC, minus 2 over 6 10 to minus 3. So time here is 4.16 10 to minus 3 seconds. Well, in the next step, I'm just gonna use this time to calculate current. So remember, current is epsilon over R, E2 minus T over RC, or just the derivative of this charge here. So when you take derivative, you'll get this equation. I just need to use this time here in this equation. So epsilon is 12 volt and R is 20 kilo ohm, and I already know RC, I already know time. From here I can calculate the current. So I have 12 over 20 10 to 3, this is 20 kilo ohm, then E2 minus 4.16 10 to minus 3 divided by 6 10 to minus 3. So this part is 6 10 to minus 4, and times this part is 0.5. So the final result is 3 10 to minus 4 ampere, or 300 10 to minus 6 ampere, or 300 microampere. So for the first solution, I'm going to use the first equation, and you will see how easy it is. So epsilon is IR plus Q over C. So epsilon is 12. Then we have I. This is the one I want to calculate. So R is 20 kilo ohm, 20 times 10 to 3, plus, you see, now we have Q over C. So C is constant, 0.3 microfarad. Now I want to calculate current when charge becomes half of its maximum value. But I already know the maximum value of the charge, which is 3.6 microfarad. I'm going to take the half of the maximum charge and divide by C, the capacitor. From here, I can directly get the current, which is 300 microampere, the same value we got in the second solution, with very less effort and time. Well, choose your way. You can have first solution or the second solution. In part B, we are going to find out the maximum current. So the current is epsilon over R, E2 minus T over RC. So at time t equal to 0, you get I as I max, which is epsilon over R. Then the maximum current is 12 over 20 kilo ohm. Then we get the maximum current as 6 10 to minus 4 ampere, or 600 10 to minus 6 ampere, or 600 microampere. It's very easy. Now in part F, we're going to find charge this time when the current is 20% of its maximum value. So here, again, you can use the second solution or the first solution. Of course, I'm not going to use the second solution, so I will use the first solution. So epsilon is IR plus Q over C. Now, I want to find the charge when I is 0.2 of its maximum value. So for I, I'm just going to use 0.2 I max times R plus Q over C. So I'm looking for this charge for this specific value of current. I know the value of epsilon, 12. I already know the maximum value of the current, which is 600 10 to minus 6 times R, 20 kilo ohm. And finally, I have Q over C. I already know the value of C, which is 0.3 microfarad. Then I get 12 equals 2.4 plus Q over 0.3 microcoulomb. So from here, Q is 2.88 microcoulomb. Now let's have our second example. Here we have a RC circuit shown here. So it says the battery has fully charged the capacitor Then at time t equal to 0, the switch is thrown from A to B. So we have the values for the capacitance and the battery. But there's one more information. So the current is observed to decrease to 0.5 of its initial value in 40 microseconds. Then we're going to find the value of charge at time t equal to 0. So this is the maximum charge actually. Then we're going to find the value of R, resistor. And also we're going to determine charge at time t 60 microseconds. And finally, we're going to determine potential across the capacitor as a function of time. So this is the discharging process, because when you throw a switch from A to B, this charging process starts. So I is I0 E2 minus T over RC for the current, and VC is V0 E2 minus T over RC. So again, remember, T equal to 0 of the discharging process is T infinity of the charging process. So right here, they have the same value of charge, epsilon times C. So Q0 is epsilon times C. It's 20 volt times 1 microfarad, and the result is 20 microcoulomb. So this charging process will start with this maximum value. So in part B, we're going to find the value of R, but before discussing part B, it's better to revisit this sentence. It says the current is observed to decrease 0.5 of its initial value in 40 microseconds. Now let's write down the current equation for that. I, right here is I0 E2 minus 2 over RC. You see I is 0.5 or 50% of its initial value. So it's 0.5 I0 equals I0 times E2 minus 2 over RC. So E0's cancel out. So 0.5 is E2 minus 2 over RC. Take the ln of both sides. This is minus 0.693. And we get rid of exponential term. We have minus 2 over RC, minus minus cancel. We already know the value of time, which is 40 microseconds. And we also know the value of capacitance, 1 microfarad. Then from here, we can get R, roughly 58 ohm. Now let's find out the charge at 60 microseconds. Well, for this charging process, charge is Q0 E2 minus T over RC. So let me write it down here. Q0 E2 minus T over RC. So what is Q0? I already know Q0. Before finding Q, let's first calculate RC, time constant. So this is 58 times 1 microfarad, and this is 58 microseconds. Now we can get Q. It's very simple. So Q0 is 20 microcoulomb. Then we have exponential term, E2 minus T over RC. So the time is 60 microseconds and RC is 58 microseconds. So it's about 1, roughly. So we have 20 E2 minus 1. So from here, charge is, this is the value of epsilon, 2.72. Then we get charge as 7.35 microcoulomb for this specific time of 60 microseconds. Now in the last part, we're going to find the capacitor as a function of time. This one is also easy, because VC is V0 E2 minus 2 over RC, or Q over C if you like. We discussed all these in the previous part. E2 minus T over RC. So remember, our V0 is actually at time t equal to 0 is the voltage of the battery, which is 20 ohm. Then I have E2 minus T over RC. RC is 58 10 to the minus 6. So this is the voltage across the capacitor as a function of time. So in the third example, we have a charging process. So a charge on the place of the capacitor is given by this equation, which is in coulomb. First, we are going to find out time constant, Then for R 4 mega ohm or 4 10 to 6 ohm, we're going to find the value of capacitor, and we're going to determine Vt across the capacitor, potential across the capacitor as a function of time, and the current as a function of time. Let's write down the main equation here. So this is the main equation. So we can get Vc, which is Q over C, and epsilon 1 e2 minus 2 over Rc. We can also write down the current dq over dt, epsilon over R e2 minus 2 over Rc. Then we are ready for the solution. Let's first put the main equation, epsilon c 1 e2 minus 2 over Rc. So I'm just going to use different colors here. Then I'm going to put this equation here, Q10 1 e2 minus 2 over 4. So you see 10 is epsilon c and Rc is 4. So your time constant is just 4 seconds. Now for the part B, since our time constant is 4 seconds, since we know the value of R, then we can calculate the capacitor. 4 times 10 to 6 is the value of R, 4 mega ohm, times C. And from here, C is 10 to minus 6 farad, or 1 microfarad. For part C, we can use this equation. Vc is epsilon 1 e2 minus 2 over Rc. But first we have to find out epsilon. For that I'm going to go back to this equation. So you see epsilon c is 10. So epsilon c is Q0, which is 10 coulomb, right? Because Q is given in coulomb. But I already know the value of C from part B. From here, I can get epsilon. So epsilon times 10 to minus 6 farad is 10 coulomb. Then epsilon is 10 to 7 volts. Now Vc is 10 to 7 times 1 e2 minus t over 4. Now part D, the current is epsilon over R, e2 minus 2 over Rc. We already know value of epsilon, which is 10 to 7 volts, divided by R, 4 10 to 6 ohm, and times e2 minus t over 4. Or this is 2.5 e2 minus t over 4. Simple question, what is I0 here? So I0 is 2.5 ampere. Question number 4. In the next two questions, we're going to combine Kirchhoff's law and RC circuit. So this is the question. So it says the circuit below was put together a long time ago so that steady state has been reached. So this is very, very important information. So we're going to find out all the currents, voltage drops across R1, R2, and R3, and charges on the capacitors. Well, for part A, first revisit this sentence. The circuit below was put together a long time ago. That means these two capacitors are fully charged. Remember what happens when we have fully charged capacitor. Let's have Q as a function of time and I as a function of time. You see, when you have a fully charged capacitor at time t infinity, a long time, you have a maximum charge but zero current. So there will be no current passing through this branch. So this branch is blocked. So this is the meaning of this sentence. So again, at time infinity or at long enough time, I0, no current passing through the resistor. With this information, we can have this simple circuit. Since this part is blocked, these two capacitors are fully charged. Current will not be able to flow through this branch. So we have there's only one branch. There's only one direction. We cannot have three different directions. So this part is blocked. Now current is moving on this path. So it's just a very simple circuit. Or we can just remove this part. So from here you can easily get the value of current. So V is I times R1 plus R2, they are in series. This is 20 volts. If you like, you can use a loop, but you will get the same thing. So it's not a very complicated circuit, so it's not necessary to draw a loop here. So V is 20 volts. I times R1 plus R2, 2 plus 3, which is 5. So here I is 4 ampere. So current passing through R1 and R2 is the same, 4 ampere. So current passing through I3 is just 0 because there is no current. So voltage drops across R1, R2 and R3. Again, very simple. So VR1 is I times R1. This is 4 times 2. It's 8 volt. And VR2 is I times R2. 4 times 3. It's 12 volt. So when you add these two, you get 20 volt. Now, so the voltage across this resistor here, R3, is 0 because there is no current. Now in part C, we are going to find out the charge on the capacitor. For that, we have to draw a loop. You can use the first window or the second window, it doesn't matter. For practice, I'm going to have both loops for you. Let's start with this one. So if you start with this window, you see there is a battery. Then when you draw your loop, you start from positive side of the power supply and you go back all the way to negative side of the power supply. Let's draw our loop. So this is direction of loop or path, and you know the rules. Let's call this one loop number 1. So the direction of the loop and direction of the current are the same. So for the loop number 1, we have I times R1. When we come here, we see a capacitor. Voltage across this capacitor is positive because I'm using the same direction from positive to negative. So it is the Q over C1. So there is no current passing through here, so there will be no voltage drop across R3. We already discussed in the previous part. The voltage for the second capacitor is positive 2 because I'm using the same sign convention, plus Q over C2. You see, I am using the same Q for the first and the second capacitor because they are in series. So when they are in series, then you have the same charge. So this must be equal sum of all the batteries on this path, which is V. Now I is 4, R1 is 2, plus Q over C1, which is 3 microfarad. Let's use just micro. Then we have Q over 6 micro. And on the right side, we have 20 volts. From here, we can get charge as 24 microcoulomb. Let's see what happens if you use the second window. Let's separate these two. There is no power supply here. Then we can have clockwise or counterclockwise direction. It doesn't matter. Let's have this loop, the clockwise loop. Let's call this loop number 2. Now for the loop number 2, you see I'm walking on this path. There is this current passing through R2. Direction of the loop and direction of the current are the same. So I have plus I times R2. Now when I come here, now I'm moving from negative plate to positive plate. So then it's minus Q over C1. So there is no potential drop here across R3 for the same reason because there is no current. Then here I'm moving from minus plate to positive plate. Then I have minus Q over C2, and on the right side there is no battery, so it must be 0. So I is 4, R2 is 3, minus Q over 3 micro minus Q over 6 micro, and 0 on the right side. So from here you get the same value, 24 microcoulomb. Now let's have our last example. So we have the same question but different circuit. Again, this circuit was put together a long time ago. Again, for the same reason. When time goes to infinity, current becomes 0. And there will be no current passing through R when you have a capacitor here. So this part is blocked. So the current cannot pass through this branch. It's blocked. So this battery is produced current. It flows around through this circuit. So this region is forbidden. Now we have this simple circuit. You see we have two batteries, but they are in the same direction. They are pumping the current in the same direction. If you like, you can use your Kirchhoff's law. So direction of the current and direction of the loop will be the same. So we have IR1 plus IR2 on the left, and on the right we have V1 plus V2 because they are connected in the same direction. So I times 5 is 30 and I is 6 ampere. And IR1 and IR2 are the same, 6 ampere. And IR3 is 0 because there is no current passing through this branch. Well, we can calculate VR1 and VR2. I times R1, 6 times 3, 18 volts. VR2 is I times R2, 6 times 2 is 12 volts. VR3 is 0. Now for the last part, for part C, let's put the direction of current. Okay, so there will be no current here. To find the charge, we can use this loop or the big one. So I'm going to start with this lower window. So you see there is a battery here. So I'm going to start from positive side of the battery and move clockwise. Let's call this one loop number 1. So the equation for loop number 1. So we start from here. So there is a resistor. But remember, there is no current passing through this branch. So it's 0. So we walk. So now you see I'm moving from negative plate to positive plate. But the conventional current for the capacitor is from positive to negative. So direction of the current and direction of the loop are not the same. Here I want to mention something important. Although no charge actually passes between the capacitor plates, but it acts just like a current flowing through it. But in reality, there is no such thing. So the direction of the conventional current for this capacitor is pointing right, but the direction of the loop is pointing left. So they are opposite. That means I'm going to use minus Q over C for the potential across the capacitor. Then I walk and I see this R2, and direction of the current and direction of the loop are the same. So it's plus I times R2. And we have a battery which is V2, 10 volt. Okay, now here I have Q over 2 microfarad. So forget about farad here again. Plus 6 times R2 is 2 equals 10. So from here Q is 4 microcoulomb. Now we can also use the big window to find the value of the charge on the capacitor. Now let me have that too. So for the big window, for the big loop, you see we have this power supply V1, and I'm gonna start from positive side of this battery to the negative side of this battery. This is our starting point, and this is the direction of the loop. Let me call this loop number 2. So the equation for loop number 2 is the following. So direction of the current and direction of the loop are the same. So I have I times R1. So there is nothing here. Then here you see direction of the loop and direction of the conventional current between the plates of the capacitor are the same. So it's plus Q over C. And there is R3, but there is no current passing through R3, so it's 0. Then on the right side we have V1, 20 volts. Remember, this definition of current for the capacitor is not real, but since it acts like a current flowing through it, we can use this information to define this positive and negative sign. So let's go back to our equation. I is 6 times 3, R1 is 3, plus Q over 2 microfarad, and we have 20 on the right side. So from here Q the same, 4 microcoulomb. So we completely finished this chapter, and I hope there is no problem on your side with this chapter.